Special relativity, formulated by Albert Einstein in 1905, revolutionized our understanding of space, time, and motion. Prior to Einstein's work, classical mechanics, based on Newtonian physics, provided a robust framework for understanding motion. However, inconsistencies arose when applying Newtonian mechanics to objects moving at speeds close to the speed of light. The results of the Michelson-Morley experiment, which failed to detect an absolute ether medium for light propagation, further challenged classical assumptions. Einstein resolved these issues by introducing the theory of special relativity, which rests on two fundamental postulates. The first postulate, known as the principle of relativity, states, "The laws of physics are the same in all inertial frames of reference." This principle asserts that no preferred inertial frame of reference exists. An inertial frame is one in which an object moves at a constant velocity unless acted upon by an external force. Prior to Einstein, Galileo had proposed a similar idea in classical mechanics, known as Galilean relativity, which stated that the laws of mechanics remain unchanged in all inertial frames. Einstein extended this principle to all physical laws, including those governing electromagnetism and optics. The principle of relativity implies that an observer in one inertial frame cannot conduct an experiment to determine whether they are at rest or moving with constant velocity relative to another inertial frame. For instance, if a person is inside a smoothly moving train with closed windows, they cannot determine whether they are stationary or in uniform motion without looking outside. The second postulate states, "The speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source." This postulate was inspired by Maxwell's equations, which describe the behavior of electromagnetic waves, and by the failure of the Michelson-Morley experiment to detect any variation in the speed of light due to Earth's motion through a supposed luminiferous ether. Classically, velocities are expected to add up according to Galilean transformation rules. If a car moves at 100 km/h and emits light forward, classical physics would suggest the light speed should be the speed of light plus 100 km/h. However, Einstein's second postulate asserts that the speed of light remains constant at approximately 299,792,458 ms/s, regardless of the motion of the source or observer. This radical assumption led to profound consequences in our understanding of space and time. Einstein's two postulates led to several surprising and experimentally verified conclusions, including time dilation, length contraction, the relativity of simultaneity, and the famous mass-energy equivalence equation. Time dilation refers to the phenomenon where a moving clock ticks more slowly compared to a stationary clock. As an object approaches the speed of light, the denominator approaches zero, causing time to slow down significantly. This effect has been experimentally verified using precise atomic clocks flown on airplanes and satellites. Length contraction describes how an object in motion appears shorter along the direction of motion relative to a stationary observer. This means that as an object moves faster, its length along the direction of motion shrinks. This phenomenon has been confirmed by experiments involving high-speed particles. Special relativity also shows that simultaneity is relative. Two events that appear simultaneous in one frame may not be simultaneous in another moving frame. This is a direct consequence of the invariance of the speed of light. If two lightning bolts strike the front and rear of a moving train simultaneously from the perspective of an observer on the ground, an observer inside the train may perceive them occurring at different times due to the motion of the train. Mass-energy equivalence states that mass and energy are interchangeable. This principle explains why nuclear reactions release vast amounts of energy and forms the basis of both nuclear power and atomic weapons. It also plays a crucial role in understanding high-energy physics and cosmology. Special relativity has been tested extensively through experiments, including muon decay experiments, where muons created in the upper atmosphere should decay before reaching the Earth's surface, according to classical physics. However, time dilation allows them to reach detectors on the ground. In particle accelerators, high-energy particles moving close to the speed of light exhibit time dilation and length contraction effects predicted by special relativity. The Global Positioning System, GPS, accounts for both special and general relativistic effects to maintain accuracy. Special relativity fundamentally changed our understanding of space and time, paving the way for modern physics. However, it applies only to inertial frames. To address accelerating frames and gravity, Einstein later developed general relativity, which extends these concepts to curved spacetime and gravitational effects. Einstein's postulates of special relativity introduced a paradigm shift in physics, replacing absolute space and time with a unified spacetime framework. The principles of relativity and the invariance of the speed of light led to revolutionary insights into time, space, and energy, reshaping scientific thought and enabling technological advancements. Today, special relativity remains a cornerstone of modern physics, continuously verified through experimentation and practical applications.